All right. Good morning, good afternoon, good evening, everyone. I know we have people from different parts of the world. So I want to welcome you to this weekly webinars on geoenvironmental engineering. We have been covering a wide range of topics such as land contamination, waste management, and sustainability and resiliency. All interested are welcome to attend. And as you know, we started these webinars during the last year, 2021. We had several webinars and they have been recorded. They are available on YouTube channel during the webinar. I will post the link to that YouTube channel. And we just restarted again webinars this year from October. So this is our webinar. Today we have very interesting webinar and we have another webinar for this year. So today's webinar, we have 827 registrants from over 50 countries. So we have a lot of people, so I recommend everyone to mute your mic and switch off your video. So type your questions in the chat box at any time during the presentation. Our presenter will answer at the end of the presentation. Thanks again for joining the webinar. So today's topic is the geotechnical stability of waste fills, lessons learned and continuing challenges. And this topic is highly relevant to many attendees that are attending today. Our presenter is Dr. Rudy Bonaparte. First of all, I want to thank him for agreeing to give this presentation in spite of his hectic schedule. Many of you know him, but I want to give a very brief introduction to him. So Dr. Rudy Bonaparte is currently chairman and senior principal at Geosyntec Consultants in Atlanta, Georgia. Previously, he served as the president and CEO of the firm for 20 years. Currently, he is also professor of practice in the Civil and Environmental Engineering School at Georgia Tech. So he received his BS in Civil Engineering from the University of Texas, Austin, and both MS and PhD in Geotechnical Engineering from the University of California, Berkeley. His professional practice has focused on projects involving geotechnical and geoenvironmental engineering, design of environmental cleanups for contaminated sites and waterways, and design and performance evaluations for waste disposal facilities. So he is a registered professional engineer in 20 states, and he is an author of 75 peer-reviewed technical papers. He has received many awards. Some of these include ASCE Terzaghi Lecture Award, ASCE Opal Lifecycle Achievement Award in Design, ASCE James Cross Medal, and many other professional recognitions. So more importantly, he has been inducted into National Academy of Engineers recently in 2007. So I want to thank again Dr. Rudy Bonaparte for taking time to attend, and thank you all for attending this webinar. Hope this webinar is informative and useful to you. So with that brief introduction, I request Dr. Rudy Bonaparte to give the webinar. Thank you so much.
Thank you for that kind introduction, Professor Reddy. As you mentioned, the title of my talk is Geotechnical Stability of Waste Fills, Lessons Learned and Continuing Challenges. While the focus of this talk is on U.S. practices and U.S. landfill facilities, I think many of the lessons are applicable to waste containment facilities around the world. The organization of the lecture is simple. It's sort of a timeline. We're going to turn back the clock 25 to 35 years and look at a few early failures of what I would call modern landfills in the United States and what we had learned by the mid-1990s, more than 25 years ago. And then we're going to fast forward to the past decade and see that we're continuing to have failures. And we'll look at the nature of those failures in these more modern years and see what kind of lessons we've learned and what some of the continuing challenges are with respect to these sorts of facilities. This is just a typical layout for a modern line landfill in the US. Beneath the waste mass, we can see a liner system consisting of a composite liner with a lower compacted clay or CCL component and an upper geomembrane component overlain by a leachate collection and removal system. We see the waste mass here. We see an intermediate cover soil layer that I've shown here, which is going to be important to some of the failures we'll discuss subsequently. And then a final cover system. If this is municipal waste landfill, it's likely that it'll have either a passive or active gas removal system, which I'm showing here. So some of the main components of a modern landfill. As geotechnical engineers, when we design these facilities, we need to be concerned about a number of static and if in a seismic impact zone, seismic failure modes. These include potential failures through the waste mass itself, failures through the waste mass and liner system along liner system interfaces, failures through the waste mass and the foundation soils, and then veneer stability failures in the cover system or the liner system along liner system or cover system interfaces between soils and geosynthetics. For today's talk, I'm only going to focus on failure modes that involve failure through the waste mass. So where did we start? Let's turn back the clock to the late 1980s to mid 1990s and look at 3 case studies, Kettleman Hills, Crossroads, and Rumpke. The first case study is Kettleman Hills, and I saw that Professor Jim Mitchell is on this webinar, and Professor Mitchell studied this failure extensively. But this is the Kettleman Hills failure. It's a waste mass and liner system interface failure, and it occurred in 1988. If we look at the liner system, shown in the graphic, at the time, this was one of the most sophisticated liner systems ever constructed for a landfill in the United States. It's a double composite liner system. With a secondary composite liner, we can see the geomembrane and compacted clay layer, and a primary composite liner with a geomembrane and compacted clay layer. The geomembranes in this case were smooth HDPE geomembranes. Textured geomembranes had not yet been invented. And we see the leakage detection system, also called secondary leachate collection and removal system, and the primary leachate collection and removal system, and various other layers. So the story here is that in early 1988, a year after filling began, and with the waste mass in an interim configuration with a height of about 90 feet, 600,000 cubic yards of waste moved about 35 feet laterally over several hours. And here we see the waste cell in which the failure occurred. Here's the actual waste mass, and I think you can get a sense that perhaps previously this waste mass had been sitting up on the back slope of this cell, and that it slid in the direction shown by the arrow here, about 35 feet over several hours. Well, the post-failure investigation revealed a translational sliding mechanism along liner system interfaces. Slippage was observed to be primarily at the interface between the HDPE secondary geomembrane and the underlying secondary compacted clay liner, or CCL. And we see that here. This is the secondary CCL layer. The secondary geomembrane that sat above it is hidden by this geotextile, but you can see the tearing of the geosynthetics and their movement down the slope. This is a photograph taken during the failure investigation after the failure, and for scale, you can see these workers here to get a sense of the size of, or the scale of the failure. Testing after, as part of the failure investigation, showed that the interface between the HDPE geomembrane and the underlying CCL had an undrained strength of about 500 PSF, so quite low. And the studies showed that undrained failure at that interface was the appropriate mode to consider as part of the back analyses. And we also found that geosynthetic interfaces were relatively weak with measured residual friction angles of less than 10 degrees. We know this information well today. There's been lots and lots of interface testing. At the time, this was relatively new to the profession, and we were learning a lot about these things. The investigations, analyses, and physical modeling that was conducted after the failure Also showed that 3D effects were important given the waste fill geometry, and that the failure mechanism involved progressive loss of interface strength, i.e. going from peak to residual strength. Here are some of the interface shear testing results from the forensic investigation. On the left, we see secondary geotextile to secondary HDPE geomembrane interfaces. Now on the right, we see secondary clay CCL to secondary HDPE geomembrane. The noteworthy thing, or one of the noteworthy things about these interface direct shear test results is at what small displacements the peak shear resistance were developed, basically in the range of 0.1 to 0.2 inches. It took only very, very small movements that can occur actually during construction and filling of the cell to go to mobilize peak strengths and then move to displacements that will result in strain softening and lower strengths. So this was something that we learned, a hard lesson to learn on the Kettleman Hills failure. So to summarize, what are perhaps some of the key lessons from Kettleman Hills? Many liner system interfaces are weak, especially if they involve smooth, high-density polyethylene geomembranes, and they exhibit pronounced shear softening with residual strengths much lower than peak strengths. Again, we know that well today. This was a big lesson learned at Kettleman. Liner system construction and waste placement operations can induce movements that mobilize post-peak interface conditions within the liner system. The potential for progressive failure must be considered in design. Waste mass stability evaluations need to address all interim waste filling configurations, not just the final configuration of the facility. As we saw here, the failure occurred during an interim configuration. And finally, this case study revealed a conundrum, and that is that CCL compaction conditions that favor low permeability and intimate contact between the geomembrane and CCL, that being compaction, needing compaction at wet of optimum moisture contents, and then smooth rolling the top surface of the clay before placing the geomembrane, which gives you intimate contact for good environmental performance. Those conditions don't favor, or I'm sorry, they also favor low interface shear strength. So we have to balance these two things. A desire to get intimate contact and low permeability for the composite liner with the potential for low interface shear strength. The second failure was at the Crossroads landfill in the state of Maine, and it occurred in 1989. This is a waste mass and foundation soil failure. We see the failure in the photo on the left-hand side of this slide. The failure started on the west side of the landfill, and it retrogressed rapidly to the west. And you can see that the failure involved the movement of a series of waste blocks, essentially riding on foundation soils beneath the landfill. So the story here is interesting. This was an 80-acre landfill with a foundation consisting of very sensitive glacial marine clay soap. It had a sensitivity in the range of 5 to 10. The foundation soil layer had an over-consolidated crust that transitioned to a normally consolidated state at a depth of about 15 to 20 feet. So with the waist height at 70 feet, and after a period of heavy rain, a rapid retrogressive slide occurred involving about 650,000 cubic yards of municipal solid waste. So it's quite a large slide. The failure investigation showed that the sliding surface was in the normally consolidated zone below the over-consolidated crust, and that the waste blocks sitting on the over-consolidated zone basically floated to the west, and they moved up to 160 feet past the limits of the landfill. So the history here is quite interesting. Recognizing the nature of the foundation soils, to maintain stability, the landfill was engineered to be filled in stages based on the predicted rate of consolidation of the clay silt layer. So they would they had piezometers in the foundation, and they would conduct periodic slope stability analyses to evaluate the factor of safety of foundation. They conducted these analyses, an update to these analyses several months prior to the failure, and it resulted in a calculated factor of safety of about 1.0. You would think at that factor of safety, perhaps they would stop filling the landfill and wait for consolidation to occur and stability conditions to improve. But notwithstanding the low factor of safety, waste disposal continued. And the owners set about a process of starting to build stabilization berms on 3 sides of the landfill, on the north, on the south, and on the east sides, but not on the west side. And this proved problematic. On the west side, the owner at the same time was making a 6-foot deep excavation to build a new landfill cell where a liner system like we saw in the earlier drawings was going to be placed to comply with new regulations. So stabilizing berms on 3 sides and an excavation on 1 side. So you can imagine what happened. The excavation led to foundation overstressing at the toe and an initial localized toe failure, and then the retrogressive slide back across the rest of the site. There were a number of challenges with the engineering here. The failure investigation showed that the foundation soil strengths were underestimated by about 25 to 30%. So the foundation was actually stronger than they realized at the time. But on the other hand, the engineers significantly underestimated the unit weight of the waste by about the same percentage, 25 to 30%. So these things kind of counterbalance themselves. And while they were measuring pore pressures in the foundation, the engineers did not think to measure pore pressures within the waste mass itself. And it turns out when the investigation was conducted after the failure that this was a very wet landfill and leachate had pooled up at the base of the landfill. So there were internal pore pressures within the system. These are 2 cross sections drawn by Dick Reynolds, who was a key part of the forensic investigation team, drawn to his best ability to scale, showing the pre and post conditions for the landfill. And you can see how the waste blocks and over-consolidated crust rode on the basically liquefied sensitive clay silt layer. So some of the lessons learned, both waste and foundation unit weights and shear strengths must be adequately characterized. That seems obvious now, perhaps didn't get enough attention at the time. Waste self-weight is by far the largest contributor to foundation loading, hence the importance of proper characterization. Again, we know that now. We didn't know it so well back then. A clear understanding of the liquid levels and pore pressure conditions in the waste fill are critical to the satisfactory assessment of waste fill stability. And each significant construction and or operational change in the field should be evaluated prior to implementing change. In this case, the excavation at the toe that apparently didn't think to evaluate what that excavation might do to the stability at the toe. And then for soft soil sites, the rate of waste filling may need to be limited by the rate of foundation soil consolidation and strength gain. This is a classical staged geotechnical construction condition that must be thoroughly understood. The third historical failure we will look at occurred at the Rumpke landfill in the state of Ohio in 1996. This is another waste mass and foundation failure. This is a large landfill, about 120 acres in size. We can see here the failure. A very tall headscarp, about 100 feet high, it stood vertically after the failure. We can see a very large run out of the waste past the original toe of slope in this direction shown here. The large run out was in part caused by the high moisture content in the waste, and in part by the fact that an excavation was being constructed here for a new line landfill. And once the waste fell into this zone, all that potential energy of the waste mass was converted into kinetic energy as it ran out down the slope. The excavation was not part of the failure, part of the cause of the failure, but it is part of what contributed to the large run out of the waste. So the story here is that starting in the 1940s, waste was placed in a ravine on the Rumpke property directly onto clayey colluvial soil that formed a mantle over bedrock. Landfilling continued until 1996 to grades exceeding permitted design grades. So those highlighted things there are important factors in this failure investigation. A week prior to failure, tension cracks were observed up near the eventual headscarp area. The morning of the slide, the toe of the landfill began to move, and the tension cracks at the crest were observed to be growing wider. And then after several hours of gradually increasing creep rates, the slope failed, starting at the toe and retrogressing to the headscarp. And this all happened in only 5 minutes and involved about 1.5 million cubic yards of material that slid, as already said, into the adjacent excavation. This drawing is adapted from a figure prepared by Tim Stark at the University of Illinois and presented in one of his papers. And we see some of the key attributes of this landfill in cross-section. The original waste mass to permitted grades is shown in light brown, and the overfilling, the filling beyond the permitted grades, is shown in dark brown. This, we're illustrating the piezometric levels leachate in the landfill as assessed by piezometers installed around the failure area after the failure, and the location of the slip surface that came down almost vertically through the waste mass, and then along the native colluvial soil layer at the base of the landfill. So due to delays in completing the lateral expansion that I mentioned a moment ago, the landfill top deck had been overfilled, and we see it in this drawing, by 30 to 40 feet in the 18 months prior to failure. And the average slope was steepened from 3 to 1, 3 horizontal to 1 vertical, to 2.6 horizontal to 1 vertical. And no stability analyses were conducted to evaluate the effects of this overfilling on the factor of safety. The failure investigation showed that the slip surface extended at a near vertical angle from the landfill crest through the waste to the native soil, where it followed the bedding of the soil layer. The investigation determined that leachate levels in the waste mass at failure were substantial, up to about 30 to 40 feet. So post-failure shear testing that we conducted at Geosyntec and that Tim Stark conducted at the University of Illinois, parallel testing programs, showed that the native soil produced fully softened and residual friction angles in the range of 20 and 8 degrees respectively. And slope stability back analyses using the leachate levels shown here and the slip surface shown here revealed a mobilized average friction angle at failure of about 12 degrees. So between this fully softened and the residual values. So the failure mechanism for this slide seems pretty obvious. It involves overstressing and progressive strength loss of the native soil due to the overfilling and the buildup of leachate levels. So what are some of the lessons learned from Rumpke? First, foundation conditions for old unlined waste fills must be thoroughly understood if additional filling, excavation, or expansion of the fill is planned. Strain incompatibility between MSW, which is ductile, and the colluvial soil, which shows very brittle stress strain characteristics, can lead to uneven development of shear resistances, localized shear softening, and progressive failure. Leachate buildup in old unlined waste fills can reduce slope stability factors of safety and contribute to the development of unstable slope conditions. They need to be monitored. These liquid conditions in the old fill should be monitored. And operational activities, in this case overfilling above the permitted height, landfill height and slopes, may reduce the slope stability factor of safety and lead to problems. So What did we learn by the mid-1990s? Through those case histories and others, here are some of the things that we learned. First, don't forget fundamental soil mechanics. Fundamental geotechnical engineering applied to all of these landfill failures. And we can learn from that. Importantly, waste materials have geotechnical properties that must be characterized. Liquid and gas conditions in the fill are important. They can create elevated pore pressures that can lead to failure or other problems. We know that well now. We didn't know it so well back then. Soil and geosynthetic interface strengths must be characterized, both the peak and residual values. Mobilized strength compatibility is often an issue. Waste, particularly MSW, is often ductile. Geosynthetic interfaces can often be brittle and strain softening. And the foundations come in all flavors. They can be sensitive, brittle, strain softening. We can have undrained or drained conditions. We can have liquefiable deposits. Progressive failure mechanisms must often be considered. Time-dependent stage loading response must be addressed at soft soil sites. Numerous interim waste configurations often require assessment. Operating conditions in the field often deviate from the original design. We need to approach expansions on top of old unlined landfills with caution and with careful stability assessments. Surface cracking and toe bulging may be considered signs of incipient failure. And communications between engineers and operators are critically important. And that's not only at the design and initial construction phase, but it's true throughout the life of the facility. So these are some of the important lessons learned more than 25 years ago. Let's fast forward now in time, and from today's vantage point, see what's been happening in the US landfill industry and at these facilities over the past decade. I'll start by saying that I'm personally knowledgeable of all of the landfills listed here. And you can see some of them have names and some of them are confidential. And they're confidential because they're private facilities and the landfill owners didn't want the facilities publicized. Well, if I've been involved or have knowledge of these facilities, I imagine there are a significant number of other facilities where there have been problems that I'm not knowledgeable about because they are confidential, but other engineers have been knowledgeable and other regulators. So I think the takeaway is that we've continued over the past decade to see a relatively large number of landfill stability problems in the United States. I'm going to talk about the three shown here. The owners have given me permission, given Geosyntec permission to talk about them. We just cannot name the facilities specifically or give their specific location. But there's a lot to be learned from each. So the first more modern waste failure occurred in 2011 at a very large MSW landfill in the mid-Atlantic region of the United States. As we'll see, this is a waste mass and intermediate cover soil interface failure. The failure occurred in September 2011 after nearly 16 inches of rain fell on this site over a month due to the occurrence of 2 hurricanes passing over the site. At the time of the failure, waste filling had recently been completed in a landfill expansion built over the 190-foot tall slope of a previously filled landfill cell. So this is the old landfill cell in here, and what we're seeing along these outboard slopes is a 100-foot wide veneer of newer solid waste that was stacked up against the slopes of the older landfill. This was a very wet landfill. Leachate recirculation at the site had been going on for years and years. High levels of stormwater infiltration occurred because of poor stormwater management practices in a very large open top deck that wasn't graded to drain. And dewatered sewage sludge, which is still very wet, even though it's dewatered, was being accepted for disposal. So all of these things contributed to high moisture contents in the landfill. Failure occurred in the expansion area in a matter of minutes and involved about 160,000 cubic yards of waste that flowed about 500 feet past the toe of the landfill. Here's the toe of the landfill, and the waste ran out this long distance here over a relatively flat area. the waste failure also retrogressed about 100 feet behind the crest of the landfill. The failure investigation showed that the slip surface was at the interface between the expansion area and the overlying waste. We could see this. This is all intermediate soil cover for the old landfill, and the failure involved sliding over this material here. Here is the toe of the landfill. A CPTU testing, 20 soundings as part of the failure investigation, were conducted around the perimeter of the failed area. And these soundings showed high piezometric levels in the expansion area waste all around the failure area. So presumably they were similar in the failure area at the time of failure. On-site observations the day after the slide revealed leachate pools and gas vents within the failure area, which were clear evidence of a wet pressurized fill. Here we see an idealized cross-section of the landfill before the failure. The dark brown is the original landfill with a liner system, a good liner system below it. I want to draw your attention to the intermediate soil cover layer that went down this entire slope. It was a low permeability soil layer. And we see the waste that was stacked up against the old landfill here, about 190 feet high with 3-to-1 slopes and several benches. And we see the location of the slip surface for this case. Now, importantly, this intermediate soil cover layer acted, if you will, as a compacted clay liner, perhaps an imperfect compacted clay liner, but to some degree prevented leachate accumulating in the expansion from percolating down into the old landfill and down to the original leachate collection and removal system. Moreover, with this condition, there was no new leachate collection and removal system installed above that intermediate covered soil layer. Here we see the failure condition after the slide, obviously, when we can see the waste mass, how it moved, and the large run out of material about 500 feet beyond the toe of the slope. So because of all the liquid and gas pressure in this facility, when it did fail, the waste more or less liquefied and ran out a long distance. So slope stability back analyses were conducted using the CPTU-derived piezometric levels and the observed failure surface as shown on the left-hand side. And these resulted in a drain waste friction angle of 20 degrees with a very small cohesion to achieve a factor of safety of 1.0. At the same time, we collected samples of the waste materials and shipped them to Ed Cabazanjian at Arizona State University to do direct shear testing in its 300 millimeter diameter direct shear box. And those tests resulted in friction angles at the appropriate normal stresses in the range of 20 to 24 degrees. And these calculated and measured MSW shear strains are lower than those for what we typically think of for municipal solid waste landfill in the range of 31, 32, 33, 34 degrees. Those are typical values that we use. So things in the range of the low to mid 20 degree range are low. And we believe that this was due to the presence of the sludge and possibly some advanced decomposition due to the high moisture content and the presence of the sludge. So what did we learn from this case study? Excessive leachate recirculation and stormwater infiltration can lead to the buildup of elevated liquid levels and pore pressures in the waste. Vertical expansions that involve the placement of new waste over old need to account for the interface conditions. In this case, a low permeability intermediate cover impeded leachate percolation from the expansion area down to the original leachate collection and removal system, contributing to leachate buildup. Either that intermediate cover needed to be removed before placing the veneer waste, or a new LCRS needed to be constructed on top of it. Very important, something we've learned over the past decade, gas collection efficiency can be greatly reduced in excessively wet landfills, both through operational problems such as the watering in of gas wells, by the reduction of gas permeability at increasing levels of waste saturation. And finally, the effects of sludge must be accounted for in the design. Adding significant amount of sludge to municipal solid waste reduces shear strength, reduces permeability, and decreases the degree of saturation. All things that can have an adverse effect on stability. So a lot of lessons learned with this case study. The second more modern waste fill failure occurred in 2012 at a large MSW landfill in the Gulf Coast region of the United States. This is a waste mass and foundation failure. The landfill cell of interest is about 9 acres in size. You can see the failure in this photograph. This is the waste mass that failed by sliding from east to west, more or less as a monolith on the clay foundation beneath it, and I'll explain that in a moment. You can see the large graben behind the failure mass. So you get a clear sense of how it moved from this photograph, approximately 25 feet east to west. So another interesting story here. The landfill cell was constructed in a deep excavation, approximately 45 to 60 feet deep, into very heavily over-consolidated native fat clay. Timeline's important. The excavation occurred in 1996 to obtain borrow soil for ongoing site operations. Liner system construction did not begin in that area until 2007. So for more than a decade, stormwater ponded in the cell bottom. So think about that from a geotechnical engineering point of view. You have a decade of water ponding on an excavated cell of highly over-consolidated fat clay. Liner system, it was a CCL on the bottom and a geomembrane on the side slopes with sand, leachate collection and removal system for both, but it was not a factor in the failure. I won't talk about it anymore. So waste filling occurred after the liner system was built from mid-2007 to early 2009, creating a slope 95 feet high with a 4 horizontal to 1 vertical inclination. Not a remarkable slope at all. Very common. One wouldn't expect slope stability problems with a slope like that. The translational movement of this slide occurred in February 2012 over a several-day period, so it was kind of a slow translational movement. 3 years after filling was substantially complete, and after 3.5 inches of rain fell in the preceding 48 hours. Here we see an aerial view of the slide. You see the graben area back here, the translational movement about 25 feet from east to west. And for scale, we see a large trash compactor, some large haul trucks. It gives you a scale of the slide area. So the first signs of a problem occurred 3 months prior to the failure when north-south oriented cracks developed at the eventual location of the slide headscarf, right in this area here. The owner-operator filled the cracks, but they were reopened with time, typically after rain events. The slide involved translational movement of about 700,000 cubic yards of waste and soil, moving a distance about 25 feet, as I've already mentioned. And the failure investigation concluded that the failure mechanism involved shallow translational movement in the native clay beneath the bottom of the liner. As part of our failure investigation, we again advanced a fairly large number of CPTUs soundings, along with 5 soil borings. 34 Shelby tube samples were taken, and from that, a fairly large number of laboratory tests were conducted, including torsional ring shear testing and direct shear testing to obtain residual shear strength values and fully softened shear strength values. And on the left-hand plot, we just see an example of some of the torsional ring shear testing that was conducted on the over-consolidated material. And on the right, the shear strength envelopes we developed for slope stability analyses. We see fully softened shear strength with a fully softened shear strength friction angle of 13.1 degrees and a relatively small cohesion as a design shear strength envelope. And for the residual value, 6.7 degrees with a very small friction angle for this envelope. Also shown on this plot is something we call the operative strength envelope. And this is the strength envelope we back calculated from slope stability analysis to attain a factor of safety of 1 at the initiation of failure for the slope. And one can see that it falls sort of midway between the fully softened shear strength and the residual friction angle of this material. We weren't able to get good data on pore pressures at the time of failure along the slip surface. We considered that the failure was under drain conditions. And so we conducted a two-part stability analysis to estimate a pore pressure coefficient to use in the slope stability analysis. We first conducted a post-failure analysis based on the 25 feet of movement, the geometry of the slide mass after 25 feet of movement, considering that at that point, the shearing resistance along the slip surface was controlled by the residual friction angle of the soil material. And with that assumption, we calculated a pore pressure coefficient, R sub U, an average value for the slip surface equal to about 0.14. This, we thought this was a reasonable value because it corresponded to a roughly hydrostatic pore pressure distribution from 0 at the elevation of the leachate collection and removal system, so that's a drainage boundary, to a hydrostatic value at the depth of the slip surface. We then took that pore pressure coefficient and applied it to the pre-failure condition before movements had started, and used that pore pressure coefficient and the slip surface location with the waste mass in its pre-failure configuration to calculate an operative shear strength of about 10.6 degrees. So between fully softened and residual values. So the lessons learned here, well, let's go back to basic soil mechanics. The decade-long open excavation allowed ponded water to infiltrate the native clay through desiccation cracks and slicken sides. This led to swelling and softening of the clay and the development of fully softened shear strength conditions in the waste mass in that zone beneath where the liner system was ultimately constructed. I should say that the failure surface was roughly in the range of about 5 to, we believe, as best as we can determine, about 5 to 8 feet below the bottom of the liner system. These stresses generated, but well, then after that, the liner system was installed and the cell was filled, and these stresses generated by the waste slope induced shear deformations in the weakened native clay, leading to progressive strength loss and ultimately failure. And to a minor degree, the buildup of pore pressures in the back end of the slope over time to the cracking that was observed was a small contributor, perhaps helped to trigger the slide. But the biggest driver was this softening of the clay over a decade prior to the construction of the cell. In summary here, a deep understanding and application of geotechnical fundamentals are essential to waste fill stability evaluations, just as they are to natural slopes and constructed embankment fills. The third and final modern landfill failure occurred in the Northeast US in early 2017. This is a waste mass failure that did not involve the liner system. We see a photograph of the filled waste mass. Here, you can see it's a large debris field. For scale, here is a large haul truck. You can see, and here's a tractor trailer and cab right in the middle of the waste mass. This failure occurred in February 2017, about 5 years ago, a little over 5 years ago, and it involved a 15-acre portion of the slope, and sadly it resulted in a worker fatality. In the weeks leading up to this failure in this area, surface cracking, slope bulging, leachate seeps, and gas venting were all observed. At the time of the failure, the owner, recognizing that had a landfill cell that was essentially cooking, was doing bad things, was trying to install additional gas wells to relieve gas pressure and improve conditions. Another very rapid failure. It occurred over about 10 minutes, starting with the bursting of the bulging faces of the outboard landfill slope in 2 areas, and then rapidly triggering a much larger slide that resulted in about 220,000 cubic yards of waste moving several hundred feet beyond the limit of the landfill. So like the case history, two case histories ago, very wet landfill, high pore pressures, waste liquefied, large run out of material. And there are other commonalities, as you see. This is an aerial photo of the waste mass. I'll first draw your attention to the green lines. These are the outboard boundary of the liner system where waste was being filled and the various cells in here. At the time of the failure, the landfill outboard slopes were about 160 feet high and an inclination of 3 horizontal to 1 vertical with some intermediate benches, very common for U.S. municipal solid waste landfills. We see in red the area of the failure, and you can see the run out distance of the waste mass beyond the limit of the liner system. I draw your attention to this roughly right-hand 90-degree angle right here at the corner of the landfill. The waste mass failed in this direction to the east, and it also failed in this direction to the south. So the faces of the landfill burst in 2 different directions. So it's important to understand the operations here. The area where the failure occurred involved an expansion of a new waste cell against the intermediate soil cover of an older portion of the landfill. So like the previous case study, again, a veneer configuration. Intermediate cover soil for the original landfill consisted of cutting some oil and gas drilling. This was in the Marcellus shale part of the United States. So there were a lot of oil and gas drilling operations at the time, blended with lime. And this resulted in a relatively hard, smooth, and impermeable layer upon which the waste was placed. And so this layer, hard, impermeable layer existed. And as part of the expansion, once again, there was no removal of the layer and no installation of a leachate collection and removal system on top of it. In addition to MSW, the landfill accepted a variety of special wastes, including sludge, which was described at the site as LSSW, low shear strength waste. So clearly they understood they had a low shear strength material. This is a drawing of or a GIS configuration of the landfill. That 90-degree angle is shown here, so we're looking at it from a different perspective. And this is a failure of the eastern face and the western face. These brown areas are delineated from the CPTU testing we conducted throughout this cell after the failure. And these are areas of high concentrations of low shear strength waste. And you can see they're set back from the face, and there's a reason for that. So the operations plan for the landfill required that this LSSW be placed at least 100 feet back from the slope to prevent leachate seeps and to maintain stability. A good idea in and of itself. But the setback limited the cell area in which the LSSW could be placed and the amount of MSW available for mixing with this weak material. That's because this 90-degree angle, quickly as you came up the landfill, that cell was getting smaller and smaller, and you concentrated all the LSSW in a smaller and smaller area of the landfill confined by this 90-degree angle. In addition, the MSW that was coming in was being used to construct this 100-foot wide, buttress zone. So that was a good thing, but there wasn't much MSW to mix with the weak material in the center of the cell. So you got high concentrations of this material. This resulted in interior zones in the cell in brown with high concentrations of LSSW. So an unintended consequence of a good idea, and ultimately a weak zone through which shearing occurred. While the landfill only accepted about 20% LSSW by total tonnage, these operational factors contributed to large areas of the cell with more than 40% LSSW. And that's important based on the shear testing that was conducted. We collected samples of MSW shown here, looks like typical MSW, and the LSSW shown here, looks like typical sludge, and sent them to Colorado State University for testing in their 300 millimeter wide direct shear apparatus. Tested both MSW, LSSW, and mixtures of the material. And the test results are shown here. And in the interest of time, not going through them in detail, what we found is that once you got to about 30 to 40% LSSW, you started to get significant decreases in the shear strength of the mixed material. And we saw we had high concentrations of the material in the cell, as we saw in the previous slide. So the failure investigation slope stability analysis showed that multiple combinations of MSW, LSSW shear strengths, coupled with estimated pre-failure liquid and gas pore pressures in the waste, produce FS values at or less than 1.0. So this explained the reasons for the failure at this landfill. The lessons learned in this case: special waste can create operational problems. Procedures developed to mitigate the problems can have unintended consequences. Special waste, if placed at too high a mass fraction, and if not thoroughly mixed with MSW or other stronger waste, will create weak zones that adversely affect waste fill stability. Low permeability zones in the waste, and this can be from intermediate cover soil layers or for other reasons, will trap liquids and gases, causing fluid pressures to become elevated. We saw that in the previous case study. We saw it in this case study. Things we've learned in the last decade. So with that, I'll wrap up with just some final observations and recommendations in light of these continuing challenges that we have seen in the last decade. First, in many ways, we continue to relearn many of the lessons that we first learned 25 or more years ago. And we need to think about the reasons. That is, we need to elevate the practice both here in the United States and around the world in our evaluation, in our operation of these kinds of facilities and the design of these types of facilities. And then with respect to all the lessons that we learned from the more recent failures, I'll identify just 5 here on this final slide. Aggressive leachate recirculation can saturate waste and cause high piezometric levels. Gas well collection efficiency can be substantially diminished in very wet landfills, leading to the potential for gas pressure buildup. And we saw that in several of the case studies. High moisture content landfills can lead to elevated temperatures in some cases. And while I didn't talk about it today, that was the case in 2 of the failures. Co-disposal of sludges and special waste can produce weak zones and inhibit leachate and gas collection, resulting in waste mass stability and other problems. And finally, vertical expansion configurations and materials can contribute to waste fill failures, and we need to carefully engineer them when those kinds of expansions are being undertaken. A few lessons learned, first with respect to leachate recirculation. We need to limit leachate recirculation rates to avoid saturating the fill and inhibiting gas collection. A proper water balance is needed to achieve that and to maintain appropriate moisture contents in the fill. And this requires monitoring of liquid levels and pressures within the waste mass. And then landfill internal drainage features must have adequate capacity to drain recirculated liquids or liquids from other sources. So this is something that needs to be kept in mind. And the types of features that need to be designed in many cases are in addition to the leachate collection and removal system. Sludges and special waste. Whenever facilities accept accepting special waste. They should develop special waste acceptance plans for each waste stream. These swaps should address potential impacts to leachate and gas generation waste properties, slope stabilities, and operations. We need to think carefully about unintended consequences of the special waste operating procedures that we develop, so that we don't have an unintended consequence. A high level of operating vigilance is needed. This is very consistent with the observational approach we use in geotechnical engineering. And finally, for vertical expansions, I think you know what I'm going to say here. The intermediate cover interface must be carefully engineered for stability and permeability. In some cases, that cover should be removed, and others, a new leachate collection and removal system should be installed on top of the cover. And finally, the effects of the vertical expansion on leachate and gas movements in the waste need to be carefully assessed. So with that, I thank you for your attention. And Professor Reddy, if we have time for a few questions,
yeah,
happy to try to answer them. I'm going.
Excellent presentation, Rudy. Thank you so much for your presentation. I know, I hear about many failures of landfills and dump sites in developing countries. I know we have participants from over 50 countries. So there are online landfills, they have dump sites, they have mixed waste, and they have no control of leachate and stormwater. I think, nobody wants to share the failures. So you have given very good information about a few failure cases. Hopefully that information will be very useful for the attendees. So I will appreciate if you can look at the chat box and take a few questions. I know we are right on time, but we can take a few more minutes and see if you can answer some questions, please.
Yes, I'm going to quickly move my camera. I have two screens. I'm going to move it over here. So let's see.
They're on the chat box.
So let's see. So I'm going to the top. Thank you for highlighting the role of liquid stormwater management, sludge, and interface. In my experience, these items are prominent factors in slides and should be systematically considered by engineers in planning field operations. And that's from Kevin Foy. So thank you, Kevin. I appreciate that comment. It is in line, and our experiences appear to be somewhat similar. What was the reasoning behind selecting torsional ring shear as a means to obtain residual strength of MSW? That plot that I showed was actually torsional ring shear testing of the highly plastic foundation clay. So it wasn't, we didn't conduct ring shear testing of the municipal solid waste, only of the foundation soils. All of the testing in the presentation that I talked about for municipal solid waste was conducted in 300 millimeter diameter direct shear tests. Question from Katie Saltanovich. On average, to what extent did the failure case studies you presented result from errors in the geotechnical analysis, as opposed to the facility staff making operational decisions without engineering input? How can geotechnical engineers prevent failures in the future? Let's just stick with the more recent case studies. It's an excellent question, a really excellent question, Katie. It was clearly a combination of things on the more recent failures. The engineers perhaps not understanding some of the consequences of the landfill taking sludge or recirculating the waste. And in these cases, the engineers knew that these kinds of operations were going to be conducted, but perhaps, and in the case of the Gulf Coast landfill, the geotechnical engineers clearly understood that the excavation was going to stand open for a decade before the cell was built, because they went out and provided construction quality assurance during cell construction. So there's an element of the geotechnical engineers having, sort of trying to think through events that might not happen. But I think to some degree, the bigger problem, particularly for the ones where the waste was very wet and the gas pressures built up, is that the owners did not engage the engineers throughout the life of the facility, and that is a problem. I've proselytized about it here over the past 3 or 4 years since originally developing some of the materials that you saw today. I think it's a very important issue. And you have operators that might not have even seen the slope stability analyses that were conducted. You know, the operators are people in the field of a part of the owner operation that, you know, that may not be cognizant that observations that could be made in the field might inform what's going on in the waste, and that the engineer could help to explain that and the significance of that. So great question. I think it gets to the heart of an issue we're dealing with in this area of geoenvironmental engineering. The two of the waste foundation slide cases presented noted movement after rainfall events. What is the connection between the noted rainfall and the observed slide? This is from Kevin Foy. You know, I think the short answer, Kevin, is they were the triggers or contributed to triggering of the slide for sites that were, you know, essentially at incipient failure. Anyway, that's certainly the case for the Mid-Atlantic slide that occurred. It was already an extremely wet landfill and was destined to fail at some point, given the conditions in the landfill waste. The rainfall that occurred from the 2 hurricanes were certainly the straw that broke the camel back. The additional loading caused by all that rainfall onto the slopes, both as dead weight and then the buildup of additional pore pressures. And it speaks to the importance of managing those things. And that is also the case for the project in the US Gulf Coast that I showed a few moments ago. Are these structures not monitored rigorously and constantly for the development of localized failures, crack development, rise in water levels? The answer is somewhat. At all of these facilities, there were observations going on. For example, if you remember, for the Gulf Coast landfill, I mentioned that the cracks were observed and they were filled in. Well, filling in the cracks is probably not the best response to when you see tension cracking at the top of a slope. It's an indication of a more fundamental problem. There were, you know, monitoring of gas wells at these sites. And if you remember the last case study, I said that the owner was trying to put in additional gas wells because they understood they were having some problems. But I think clearly, while some data is being collected, in each of the cases, there was not a systematic approach involving knowledgeable engineers who could help to understand and explain what was going on with enough time to have a response to prevent the failure. You know, these cells are so big, they get to a point where, you know, it's almost too late to do anything. So the need for a response needs to be early when one first starts to see indicators of performance problems. A very good question.
We'll take a couple of questions, Rudy, and then just take a couple of questions, 2 questions, and then we will end the webinar. I know there are a lot of questions here.
Okay, I'll take the next one from Jagadish. If 2 of the landfill cases included stormwater buildup and high pore pressures, and given the increase in frequency of abnormally high rainfall events due to climate change, should we expect more such failures in relatively older landfills due to stormwater infiltration? If yes, what could be done to avoid such failures? The answer to that is yes. Another very good question. You know, we also have a lot of landfills, not only rainfall, but we have a lot of landfills that are located near rivers or located near the coastline or near estuaries. In the old days, so to speak, landfills would be created in wetlands. People didn't recognize the value of wetlands, and these would be adjacent to estuaries. So they're in terrible sites, and we're getting, a sea level rise, more intense storms. This is in the United States, a big concern to the US EPA. They're thinking about it. I don't know how they'll ultimately address it, but for owners and engineers, yes, we need to have, very good stormwater management systems. And owners of old closed landfills don't want to go back and install those. So, that's going to be a challenge. There may need to be additional engineering measures for older landfills that are located adjacent to estuaries, rivers, other water bodies. So, like many areas of infrastructure, climate change, global warming, sea level rise, all those manifestations are going to have an impact on facilities that will need to be monitored and addressed. Landfill southern US, if there was ponded water at the base, the desiccation cracks should not have formed. Well, I think one has to remember that the rainfall is intermittent. This is an area of very, very high evaporation. So you get rainfall, you get evaporation, you get rainfall, you get evaporation. Perhaps ponded wasn't the right word in terms of continuous ponding over the 10-year period. You'd get a lot of rainfall, there'd be ponding for a while, it would dry out in the summer, you'd get desiccation cracks. So it's a seasonal, even weekly, cyclic kind of activity. I can stop or keep going, Professor.
I think, there are many other very interesting questions. So what I will do is I will save the chat box and comments and then send it to you. Maybe I also ask whoever, ask those questions to contact Dr. Rudy Bonaparte. He will be happy to answer you. I don't want to keep everyone staying late. So yeah, I appreciate taking some questions, Rudy. There are, a few other questions in the chat box, but, because of the time limit, I will defer those, to be answered through emails. So again, on behalf of all the attendees, I want to thank you very much for taking your valuable time and enlightening, all the attendees about these issues. As I said, these are very, very important issues that needs to be addressed in developing countries. You have enlightened quite a bit with this one. So, and I also want to thank all the attendees taking time to attend this webinar. Any last minute comment, Rudy?
Well, thank you. I appreciate everybody taking the time to be on the call with me, and I will thank you, Professor Reddy. I think having these webinars this semester is a really nice thing to do for the profession. So I'm grateful to be included in the program.
Okay, thank you so much. So with that one, I want to end the webinar, and I will see you next week. We don't have a webinar because of the Thanksgiving, and a week after that is going to be our last webinar for the year. So thank you very much, everyone.
Bye-bye.
Bye.